So one thing I need to cover, this is all echoes of what you've done in chemistry anyway, but I want to get the ideas out there before we actually get into water. And that is, you write a chemical reaction as an arrow or possibly as a double arrow. And what you're starting with are either reactants or substrates. There could be just one over here, there could be a number of them over here. Now, substrates tends to be the convention for biological reactions, because very few biological reactions happen where the reactants are not stuck onto an enzyme that's helping them react. And when they're stuck on an enzyme, they're called substrates. What you have here are things that help the reaction happen. And so they could be an enzyme. It's basically things that don't change. They don't come out changed. They might change in the course of the reaction, but they'll change back. And so they could be an enzyme, they could be light in a photosynthetic reaction. There's a whole bunch of different things you might put on the arrow, just as a message that this is necessary in order to get this thing to happen. And then at the end, you get one or more products. It is that the reaction produces those. And it's a very simple representation, one that I'm sure you know from chemistry, but I wanted, because of the substrate bit, which you might not have had already, I want to get that out there. Okay, on to the third chapter, which is on water, which to some extent is probably the last chapter that's going to be very strong echoes of what you've had in chemistry already. So here's water as a bipolar molecule. Because the electron shared from the hydrogens, the electrons spend more time around this larger mass of protons, then they tend to make this end of the molecule more negative. Not fully negative, but more negative. And because they're spending less time here, this end of the molecule is positive. And because these things arrange themselves with a certain angle, you wind up with two ends, a negative end and a positive end, a bipolar molecule. And that's pretty much what makes water do all of the pretty unique things that water does. Oh, sorry, there's a dragonfly buzzing around the class. It must have come out of the pond tank. Boy, is its timing bad. We'll go through the features of water one by one. First is its feature as a solvent, is that every time I put this down here, it reminds me of an old cartoon where two scientists are kind of looking at a piece of paper that the scientist sitting down has, the other scientist looking over his shoulder. And the scientist that's sitting is saying something. And he's saying, well, I'm pretty sure this is a universal solvent, but I can't figure out what to keep it in. If you produced a material that could dissolve anything, you couldn't come up with a container for it. Well, again, variation on it. That's a chemistry dad joke. Water is an incredibly effective solvent. Lots of stuff dissolves in water because lots of stuff is polar in one form or another. Ions are not polar, but they are charged. Charged particles dissolve in water. Things that have unequal distributions of electrons to a large extent will dissolve in water. So it dissolves a lot of stuff. And the things that dissolve are called solutes. And what you wind up with is a solution. In this case, what's called an aqueous solution. And you'll very often see parentheses AQ as a signal that you're dissolving something in water. Okay, I need to. Well, I'm going to write this and then show it to you. Water works through something called a hydration shell. And because it's on video, I can move this even if you haven't quite copied it yet. It's on the picture here too. So you put a cube of sodium chloride, salt, into water. There's your cube. The water molecules start to be attracted to the two different components. The chloride, which is a negative ion, and the sodium, which is a positive ion. On the periodic table, sodium's here, chloride's here, so chloride's bigger. It's a bigger atom. That's why they're represented that way. But it will gradually wedge the ions off of the cube and it will surround them. So this little positive chloride, the negative ends of the water molecule are now all around it in 3 dimensions. That's why they call it a shell. And it separates it from the chlorides and it keeps it in the water. It dissolves it. It's not going to settle because it is always surrounded by the working spheres of water, a hydration shell. And that is the secret to how water dissolves a lot of stuff. Some molecules will dissolve in water, but they're big enough that the hydration shell can't completely keep them moving in the water. Things like starch will settle out. They are somewhat polar. They do dissolve, but they don't dissolve great. They will settle. So this varies according to the features of the molecules or the ions that you're dealing with. A related feature of water is that it sticks to things. It shows adhesion. You have a puddle of water and you stick the corner of a paper towel into it. The molecules of water stick to the molecules of starch in the paper towel, and for reasons that'll come up in just a second, pull more water in behind them that sticks to more molecules of the paper towel, and eventually the water on in the puddle will move into the paper towel. You may hit a point where the pull of the water on the water behind it isn't strong enough and you only get part of the puddle and the puddle separates. In that situation, you're dealing with another property of water. But I gotta get 2 more terms down here first. Things that show that attraction, that adhesive attraction to water, are called hydrophilic. Literally means water liking in Latin. Things that are not attracted to water are hydrophobic. You put them into water and they separate out. They don't dissolve. They don't go into solution at all. Is it fats, lipids are like that. Mineral oil, regular oil are hydrophobic, water disliking materials. I'll get it on here. Since water molecules have charges on each end, they also are attracted to each other. In a liquid form, the attractions are transitory because the molecules are moving fast enough. Basically, the three phases of matter reflect how quickly the particles are moving. If the particles are moving so quickly that they can't stick to one another, then if they're really moving completely freely, you got a gas. If they're moving with some connection to one another, you have a liquid. And if they're kind of locked together, then you have a solid. Same thing's true for water, is that in its liquid form, the water molecules are connected to one another, but the connections make and break and make and break. With advanced technology in the last few years, they've actually shown that in a glass of water at room temperature, you have little clusters of molecules on a molecular level that are actually kind of locked together. Again, it's transitory, but they're not all completely free floating. You get these clumps on a molecular level, and the cooler the water is, the more clumping you get. This connects to the concept of heat. What you're measuring with temperature is on a molecular level, on an atomic level, how fast are the particles moving? The energy of the particles, the speed with which they're moving is heat. And if they're absorbed, that energy is absorbed into a thermometer. It makes those molecules of either alcohol or mercury in the thermometer move faster. When they move faster, they bounce off of one another more often, and they tend to push each other apart. So as you warm things up, materials tend to expand. As you cool things down, materials tend to get more dense, they contract. It's just a feature of the particles either hitting or not hitting each other very, very quickly. Water is a little weird this way. As you cool water off, the molecules don't push apart each other as much, and it gets more dense. So cooler water is more dense than warmer water. But these have charges, and the charges involve a certain amount of repulsion too if you crowd them too much. So you get them down to about 40 degrees Fahrenheit, about 4 degrees Celsius. And as they get near one another, instead of continually bouncing off and bouncing off, they tend to kind of flip and connect with hydrogen bonds and kind of lock together. But when they lock together, they actually push each other apart a little bit. So as you go below 4 degrees, more and more of the liquid water isn't liquid. It's little packets of expanded crystals of water. In liquids, there's some connections, but they're moving too fast to sustain those for long. As they move slower, they can set themselves up with this lattice work, stable hydrogen bonds, but it produces more space between the molecules. In order to get it so that the molecules are really locked together in a stable crystal, you got to get it a little bit cooler. Got to get it down to 0 degrees. And then below 0, it's locked together as ice. So what happens with water that has a surface? Well, the molecules at the surface tend to not hit each other as much because there's no three-dimensionality there. So they tend to not space out quite as much. They are a little bit more locked together. They're a little bit denser. They produce kind of a dense layer right on the surface that a piece of paper will float on, or a water strider can spread its little hydrophobic bristles across, and it'll actually support the water strider. That is surface tension. The molecules are closer together, though. If there is a surface, there are molecules in the water that are heading for the surface. They're being grabbed by the other molecules around them as they go. And the surface is a little denser, so getting through it and getting out into the whatever's above, whatever the gases are above the surface of the water, only the very fastest moving water molecules are going to be able to make it free. That is evaporation. Water is an incredibly good cooling system when it evaporates, because it takes a decently hot water molecule to get free and take that heat with it, right? If you put nail polish remover, acetone on your finger, heat it up. Acetone is not terribly cohesive, and it doesn't have much of a surface tension. It evaporates really easily. You can feel the heat go with those molecules, though. It's just that it evaporates really easily. When you sweat onto the surface of your skin, then you don't really necessarily feel it evaporate out. In order for the water to get into the gas above it, it's going to have more trouble if there's already water molecules up there in gas form, water vapor floating around. Evaporation is slowed down depending on the humidity of the gas above the water. So when it's a really hot, humid summer day, you're sweating, but your sweat isn't evaporating terribly effectively. It is evaporating, it is cooling you off. But this time of year, when it's nice and dry, you are still losing, sweating a little bit, but you barely even know it. It evaporates so quickly because it's real easy for it to get free into the gas. But it's a nice cooling process. Whether you're a dog panting, or a crocodile on a hot beach with its mouth open, or we're sweating onto our surfaces, it is a good way to modulate temperature, to get rid of heat. If you have a container of water, you do not have a container of water. It is not pure water no matter what you've done with it, because at any given millisecond, some of the water molecules have dissociated. They've fallen apart. One of the protons has come free. It's now a hydrogen ion. It's a proton with no electron. It's H+. And it's left the electron behind, so there's an oxygen and the remaining hydrogen with an extra electron, OH-. This is hydroxide. And this is the ionization of water. And in your glass of pure water, that's how much of it has ionized. One times 10 to the -7. But what you have is equal amounts of positive ions and negative ions. So if you're going to measure the positivity or negativity of the water, it's neutral, it's balanced. We're talking about pH, little p, big H. What the P stands for, various books will tell you different things. I learned proportion of hydrogen, and the number comes from that negative exponent. They were nice enough not to make it a negative scale. But that's where the number comes from, is a -7, pH of 7. If the proportion of hydrogen gets bigger, then the number of zeros in this gets smaller, right? 0.1 is a much bigger number than 0.00001. So 0.1 would be a pH of, that'd be 10 to the 1, is that pHs don't really get that low. But a number that's lower is more hydrogen. And more hydrogen is the way that we measure an acid. More hydroxide is the way we measure a base. So as the pH goes down, the proportion swings toward the hydrogen ions. As the pH goes up, the proportion swings toward the hydroxide ions. And it's a logarithmic scale. It's a base 10 scale. So every number is a 10-fold change in whatever we're looking at. It's a 10-fold change in hydrogen concentration at the lower end. In this case, the upper end, I don't know why they did this way. And a 10-fold increase of hydroxides at the upper end, the bigger numbers, right? As more and more zeros, a smaller and smaller number. Now they could have made it the Poe scale, proportion of hydroxide, and then it would work backwards. But they had to pick something, so they went proportion of hydrogen, which gives you indirectly the proportion of hydroxides. Give you an idea. This you've done, I suspect. And this one makes more sense. You've got the high pHs here. This is the basic end. They used to call it alkaline. You'll see alkaline as a term sometimes. More OHs, oven cleaner, household bleach, household ammonia. Get down. Seawater is somewhat basic. Human blood is somewhat basic. Here's pure water. Then on the acid end, you get urine. We tend to flush a lot more hydrogen ions out of our blood to keep our pH balanced in our blood than hydroxide ions, so it makes your urine a little bit more acidic. Tomato juice, grapefruit juice, lemon juice, stomach juice, and more hydrogens. So it's just basically the way the scale works. And it's a part of the nature of water. And why is it important? Because big biological molecules are often held into a particular shape by hydrogen bonds, little charge attractions inside a bigger molecule. If you expose those big molecules to these little bitty ions, hydrogen ions and hydroxide ions are tiny, but charged. They can get into these bigger molecules and disrupt the connections that are holding the hydrogen bonds together. That's what your stomach acid is there for. Your stomach acid doesn't digest anything. It disrupts the big molecules, unwinds them, because what you're going to need to do is snip them into pieces. And we do have one chemical in our stomach acid that once they're unwound, it'll snip them in a couple of places. And that's purely because when that molecule moves from your stomach acid into your intestinal basic environment, some of those molecules would go whoop right back into the hard to digest shape that they came in as. But now you've snipped them into bits and pieces so they don't do that. So we have one enzyme in your stomach acid that hits one connection inside these bigger molecules and just snips them in a few places so that later you can break them down into individual components that you'll absorb. Okay, that is basically the water chapter. And next we'll get into organic chemistry, which will probably be the beginnings of the new stuff for people from chemistry background.